Okay, so I'm gonna keep going about the Wahlfarth model, which one is very important to understand the monetization dynamics, very basic one. Okay, in a previous class, we learned about the base of the Wahlfarth model, with the assumption of the single spin. Wahlfarth model implies we talking about the single spin, or in other words, it's macro spin or monodomain or coordinate location. So that means we don't care about the creation of the multi-domain. So it is too much simple, but still we obtained many important features. So we can understand many important results from the Wahlfarth model. So as I already mentioned, we talking about the single domain, and also we assume the Unitian anisotropy. So the total energy of the system can be written by this equation. And we already explained about how we can obtain the stable direction of the monetization by solving this energy equation. Yeah, here the monetization direction is defined by angle phi from the field direction. And this field direction is also misaligned from the EG-axis by the theta. So we have to solve the energy equation with respect to the angle phi to find the energy minimum point, or in other words, stable point. So for easiest way, when theta is 0 means the field direction is aligned to EG-axis. That's the most important case actually. Or sometimes we can apply the theta is pi case, which one is the antiparallel case, so EG-axis. Then we can simplify this equation. So by the first derivative, we can obtain this relation, and that means we have two solutions. Sine phi is 0 or cosine phi satisfied this relation. And we also considered about the stable condition, not the equilibrium condition. So they should satisfy the second derivative must be positive. So when we take in the second derivative, we can obtain this relation, and we have to think about these two solutions. Yeah, this is and this is the second case. So let's think about the first case. The first case means phi is 0 or pi. And when we substitute these two cases in the second derivative, we obtain this relation. So when they satisfy the positive, that implies they are stable. So when the field is larger than they are stable. But if they are less than this value, that means they become unstable. So in other words, this state is no longer stable. So we need another stable point. So that implies there is some switching. The same thing happens in angle phi is pi. Yeah, only the difference is sign. So when h is larger than, is smaller than, then they are stable. But if h is larger than, then there are another switch conditions. So that implies when h is positive means angle phi is 0. So they are the same. When field is have a negative sign, but less than this value, then they are still stable. But when field is smaller than this value, certain value, they are no longer stable. So they are switching back to the other direction. So when we increase the field again, before the field strength is reached the critical point, they are stable. But at this certain point, they are switching. So that field is called coercive field, or it should be this relation. Okay. And also we have to consider the second condition, but when we insert this relation, it's always unstable. So this is not a meaningful solution for this case. So in this calculation, we obtain the switching field or coercive field, or we call balance field is 2Ku over mu0 ms. Yeah, that is a very important relation, or we are using this balance field in many times. So in that relation, this one also mu0 ms hk. Here mu0 ms hk generate the energy density. Means the unit is joule per meter cube. And in the right hand side, 2K is also energy density, unit of energy density. So when we obtain some kind of field, they always have this form. Some field must be 0 ms and some energy term. Yeah, they are always we can define such kind of effective field for each energy. Okay. Okay. So now we are think about the more general case for the general angle. This result is about the field is applied this z-axis. Now we are talking about the general case. So theta is no longer zero. So that implies the energy equation is not that simple. So let's introduce normalized field H. Small h is divided by external field divided by this energy field, which one is defined by previous page. So we are using this HK many times. So please remember that the definition of HK. So the normalized energy, we normalize energy by Ku, 2Ku over V. So the energy equation is very simple. It's just the sine and cosine function with the normalized field H. Okay. Okay. Yeah. Let's do math again. Let's take the first derivative by to find the energy minimization or equilibrium point. Yeah, when you take in the first first derivative, we can obtain this form and plus h sine phi. They must be satisfied at 0. But as you see here, if the theta is 0, we can obtain the same result in the previous case. But with the non-zero theta, it is not solvable, unfortunately. So just move on to the next step before finding the solution. Okay, another important point is the stable condition, which means the second derivative must be positive. Okay. Actually, by solving this energy minimization solution equations, we obtained the direction of the magnetization. So let's think about that. For a given field, yeah, let's fix the field. We obtain the direction of the magnetization from this relation, but it's not easy. So is the angle of the magnetization, which one you want to find, is the function of the external field and the theta. And also we think about that the small m, if this is the field direction, and this is the z-axis, and this is the, let's say, the magnetization direction, and angle phi is defined here, direction from the field to the magnetization. So this is angle phi, and cosine phi implies the projection of the magnetization to the field direction. Let's say this is small m, and this small m is defined by its normalized value also. So cosine phi we can replace by the small m. And in this relation, we can find we can replace the sine phi by plus minus root 1 minus m square. Okay, and by the simple expand of the sine function, the sum minus of the sine function, you can rewrite this form. And also this sine to phi by the function of m and root 1 minus m square. And here cosine to phi is 1 minus 2m square. Okay. And we have to solve this relation. We have to solve this equation. Yeah. So let's think about for given angle theta. If the direction of magnetization is fixed, we can find the solution m from this equation. That is not easy. So let's back to the easiest case when theta is 0 and phi again. And in that case, theta is 0 case, then it is 1 and this is 0. So that implies the m plus here, m plus h, we have a common point, root 1 minus m square, m, and n, we have m plus h here. And also, in this relation, we can find to satisfy this zero condition, they should satisfy m is minus 1 or m is minus h. Actually, that result is the same on with the previous calculation. So let's think about the stable point again. When theta is 0 and pi, can obtain this relation from here. And when m is minus h, it is never stable. So it is not physical meaning solution. And when m is plus minus 1, we can find this relation that implies h is satisfied when h is larger than 1, h is smaller than -1, that is the same result in our previous result. This relation. So that implies when theta is 0, we can obtain this square hysteresis loops. And the switching point, switching field, is still same result. And let's think about that when theta is pi over 2. That implies we applied field to the hardest direction. So in this case, when theta is 0, 5 implies we applied field to the EJ direction. The second case is we apply field to this direction. Not the EJ. Here is the EJ. So in that case, yeah, let's starting again the energy equation. Yeah, that's the first derivative of the energy equation. And let's think about this case. So this term is going out, it's 0. And this term generates -1. So we have a minus sign here. Please compare to this case. Only difference is the minus sign. So we also have a solution, m is ±1 or m is h. And also think about the second derivative of the energy equation. So when m is h case, for the second derivative, we can obtain 1 minus m squared, that is the sine square of the phi. So they are always positive. So that means they are stable solutions. And also, m is ±1 implies when h is smaller than ±1, and also they satisfy this relation. So that implies m is h implies this one. This relation. So that means the magnetization direction to the field, I mean, here, if we have a zero field, magnetization is aligned to the EJCs. But when applied field to the hardest direction, the magnetization is there's some small rotations, and the projection of the magnetization is exactly proportional to the external magnetic field. Yes, that means it's linear. And the M, they are linear. When the magnetic moment is smaller than the saturation value. But when they are saturated, that means they are ±1. There is some saturation. So we think about two extreme cases, the hard axis case and then easy axis case. And the saturation field is the same. For the hard axis and the easy axis. Okay. And how about the other angle, like 10 or 45 or 8? Yeah, you can easily imagine. Now you can easily imagine such behavior. The angle 10 degree means the field is applied just a little bit is aligned from the z-axis. So they should behave like z-axis, but small difference. So there is some small change of the loops to 10 degree. And the 80 degree implies the field direction is little bit off from the hard axis. So they should be similar to the 90 degree. So they should be something like this. Yeah. So that is the result of various angles. Unfortunately, if set these two extreme case, the hard axis or z case, yeah, we cannot solve this equation easily for degree or 45 degree, but we can imagine such behavior, such kind of shape of loop. Okay, so for the general case, this is the general solution. For the normal field and the magnetic moment, they have this behavior. Here there is some switching, and then saturate again, and then come back here to here. Yeah, that is the 45 degree case. Unfortunately, we cannot solve that one for the general angles, but numerically, it is not so difficult. So that is the one example. That is the result of the calculation of Wahlfarth model. Here, the angle is changed. From 0 to 90 degree, I just calculate, solve the Wahlfarth model, and this blue one is the field direction, and the red one is the orthogonal component. Yeah. Okay. So you see here, the cohesive field is starting from the maximum, and then they are decreasing, and then the saturation field is same to the cohesive field. And let's think of the switching conditions. When they are close from the second derivative of energy, positive to the negative means, we already mentioned that several times, they are stable, they are unstable. So the switching occurred when they are close from plus to minus. They should satisfy zero condition. And then let's think about this second derivative of the energy again. And this is the switching condition, switching field. Okay, and this is the equilibrium condition. So by combining these two equations, yeah, this is the equation for the angle phi and theta, and but now we want to find the HS. So by combining this two equation, you can obtain this relation. You can eliminate the angle phi, then the switching field is the function of the theta here. And this theta also we can replace by the cosine theta to the h perpendicular direction and sine theta to the h parallel direction to the z-axis. So we can replace h cosine theta by h perpendicular, h sine theta to the h parallel. We can obtain this relation. And this relation when we plot to the H perpendicular to the H parallel, they have this form. That is called switching condition of the anti-moment to the depends on the field direction. That asteroid curve, this curve is called the asteroid curve, is very important in a spintronic devices. Okay. So it's called asteroid curve, and this implies here when we apply the field to the EJ-axis, the loop shape is something like this, very square. And the switching field is 1 by the normalized field. Okay. And then the switching field is decreased by changing the angle. And then increase again. This is the curve of the sternal field is the same to the 1. Okay. So that curve implies path. Okay. And the other curve is not the sternal path model, but by some curling model. So this is beyond the Wahl's curve. So just ignore this part. Yeah, just let's back to this asteroid curve again. So this curve implies when we applied the half field here and here, then we'll be here. So in order to occur the switching, if we applied half of the perpendicular field and half of the parallel field, then they're switching. So each one is less than the switching field, but we can obtain the switching by applying the half of the perpendicular field, half of the parallel. Okay, so that's the key idea of the M-NEM switching. Yeah, just remember that. I hope you students remember this magnetic core memory. Can you remember this photo? Student, please answer me. Can you remember that photo? Yeah, I showed that photo very early stage of our class. Yeah, that is the magnetic core, and there's some line, and their size is order of millimeter. So the old lady made this kind of memory by the stitch. But let's think about these things. We have two ferromagnetic layers, and there's some tunneling barrier. And we didn't learn, but there is some called TMR. It's kind of MR. And so the magnetoresistance, the resistance of this element, depends on the direction of the magnetization. When they are parallel or anti-parallel, the resistance is changed a lot. So when they made such kind of element by the array system, if we read this resistance, we can obtain the status of the direction of the magnetic moment of each element. So that can be a basic principle of the memory things. So when we read, there's some read current here, and can make such kind of circuit. We can read this point. But how we can write it? Yeah, that's the asteroid curve here. we send current to this station and this station together. Then this red one, this cell, the switching condition here. But the other cells, there is only one field. So we are here. So they are not switching. These cells are not switching, but only this red cell can be switching. That's the basic of the field driven the MNAM. So it sounds good. So people investigate this kind of device a lot, very, very hardly at the end of the last century. But unfortunately, this curve is different for each cell. Because even though we made this cell identically, but in reality, there is some kind of inhomogeneity of the materials and the etching procedure and many, many things. The analysis field of each cell is a little bit different. So the real acid curve of each cell is something like this. So when you apply field, only direction here. Unfortunately, some of them are switching. That's called the unwanted switching. So in principle, this field-driven MNAM should work, but when we made a real device, there is some kind of certain failure rate. So many people imagine, okay, that's the engineering problem. We can solve it by the control procedure. So people spend a lot of time and money and effort to solve the problems, but finally, people gave up. Yeah, we cannot make a good device because if we make the gigabit one, the billions of the cell must be working. That's not easy one. So people gave up to MNAM, and that's the crisis of the spintronics. Because this MNAM is one of the biggest device for the spintronics. Then, surprisingly, there is a new technology is invented called spin transfer torque. Which one is very important? Then we can solve such problems. But still, we have to understand this asteroid curve because it is very basic in a field-driven manipulation dynamics. Okay. So let's back to the small parts model again, and the energy equation here. Yeah. When H is the zero, this energy profile implies. So let's think about that. This point is very stable one. So there are stable point here or here or here. Actually, this is the same angle to here. When we increase field, small field, the normalized field from 0 to 1, to the -1, each curve is something like this. Yeah, when we h is minus 0.1, the energy level here is a little bit increased, while this energy is a little bit lower because the minus sign implies they prefer the 180 degree. And when we increase the absolute value of the H, let's say minus 0.5, we have something here. This energy is much stable than here, but the magnetic moment is switching from here to here, we have to overcome this energy. Yes, this energy barrier is corresponding to the switching field. So that's why we are getting smaller and smaller energy when we increase the external field. And even the H is minus 0.9, the energy value is small, but still there is a finite energy. They are still here. And eventually, when H is minus 1, they are falling down to here. The switching is occurred. This is for the when set as 0 case. Okay. Yeah, we are here. Okay. And how about when set as suddenly? Then implies we are applied field to the 30 degree from the EG axis. So when H is 0, energy is here, and as you see here, the stable point of the monetization is 30 degree. There is some shift of the this curve when H is 0. But when H is, when we decrease H value, the energy profile is something like this. Okay. And as you see here, the energy barrier is getting smaller and smaller, and the switching is occurred somewhere here. Okay. Then we have a switching here. So the required field for the switching is not the switching is occurred somewhere minus point something. So the switching field is getting smaller for the set as 30 degree. And this another thing is the energy profile is quite asymmetric. For example, here, this curve, like this, right? Actually, in this case, they are truly symmetric for this line. Yeah, they have a 180 degree symmetry. But here, definitely there's no symmetry. And even we shift the axis here, there's still asymmetry because we have this point. Okay. Okay, so now I explain about the Wahlfarth model, which one is very important. But as I already mentioned, they are too simple. So we are missing many important points, like a domain wall motion, or the pinning of the domain wall, or effect of the defect, or non-uniformity of the samples. And also, we have many cases we obtain the incoherent rotation. That means, in other words, curling means if we have the material here, the spin direction of one point here, but the in the bottom they have a little bit different angles. So there is some continuous variation of multiplication angles. That's what we call the curling. And also, this model can be applied to the switching of the spin transfer torque and NEM also. But the simple case, we can obtain very simple relation like a Wahlfarth model. But in a realistic case, it's much complex, and we have to apply. We have to obtain more. We have to apply more complicated models to obtain the realistic behavior. Okay. And there is another important thing called the Brown's paradox. Yeah, we mentioned many times the analytic field HK, which is defined by this relation. But in real experiment, the observed Cauchy field is much smaller than the HK. That's what we call Brown's paradox. That implies failure of the macro spin model, and that can be happens because of the nucleation of the reverse domain at the imperfection point. Yeah, so that means the coherent reversal model or macro spin or single domain model is not is unrealistic for realistic case because the defect or edgy or incoherent rotation and curl effect is sometimes dominant. So that's why we need a micromagnetic calculation. We perform the micromagnetic calculation in many cases to obtain the behavior of the magnetic moment. Yeah. So yeah, but this is a little bit too much for this introduction course. But I want to show some example. This is small arrow implies the direction of the magnetic moment of each small cells, and as you see, the direction of the magnetic moment is not the same for all points. They are pointing out a little bit different directions, and when the switching occurred, they form the multi-domains. So this micromagnetic simulation plays a very important role in research of the spintronics, and that implies we can solve the magnetization equation called the energy equation, which one we are gonna learn next class. And there are many free software. You can download it from the internet without any cost. And there are many good softwares, and also by virtue of the powerful computing power of the nowadays, we can calculate the micromagnetic simulation by your personal computer or your notebook. And the good thing is, when we play with the micromagnetics, if we increase the size of your sample, the required computing power is increased very fastly. So it is good for the nano device, which one is very interesting. Okay, and yeah, there are many things about mathematics, but now it is too much in this stage. So just to remember that the strong alpha model is very powerful, but there are many limitations. To overcome that kind of limitations, we need micromagnetic simulations. Okay, so any questions about this today's strong alpha model calculations? Okay, so let's move on to the next chapter. Okay. In the end of the strong pulse model, I slightly mentioned about the M-name structure, but there are many things you have to understand to understand the MR, the M-name. So in this next chapter, I want to talk about the various magnetic resistance called the MR. And also, there is as you see here, there are many MRs. It's called the GMR, or another important thing is TMR. And there's an application of the GMR or TMR for the hard disk drive. And also, I'm going to explain about the MNAM. Okay, so the MR implies the magnetic resistance. That means the resistance of your sample is changed by the magnetic field. Then we call this the MR. The first, before learn about the MR, you should understand the Hall effect. Hall effect was discovered by the Edwin Hall at 1879. Surprisingly, this because this founding is before the electron was discovered. So they just experimentally observe such effect, but they don't understand what happens inside of their samples. And the funny thing is, he found this important finding during his doctoral degree. So in your age, okay. And there is many good sources about the holy pet. I'm gonna show this one. Maybe I can start this one. So
Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and the Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate, and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of only few microvolts per Gauss, so therefore these devices.
Okay, I think that's enough. Okay, so there are many good animations of the Hall effect, so you can easily understand what is the meaning of the Hall effect and the basic principle and applications. So here is more details. Okay, so think about such kind of conductor, and we apply some external voltage here, and we have a charge current. When we apply the external field, let's say the z direction of the or perpendicular of this then there's a Lorentz force. Yeah, Lorentz force because of the external magnetic field. The direction of the force is cross product of the velocity, which one is the same direction of the current. And the cross product of the B field generates the perpendicular force. So the electron with the external field, they are bending. The direction is, the trajectory is bending. So as a result, we have a such kind of trajectory instead of this direction. Okay. And if we have a g-axis V field, and also we think about the steady state. By the bending of this direction, there's because of the lack of the negative charge. So that means we have a extra external field to the y direction. So in a steady state, there is a balance of the field, the force between the y field, y direction external electric field, and the force because of the magnetic field. So they should satisfy this relation. Okay. And this relation, we can obtain the voltage across this y direction, this V hole. And this is the EY multiplied by width of your sample W. So this is EY. You can obtain this relation. And the Vx is, we can rewrite here. The current I is the current density multiplied by the area, the cross-section area here. W is the width and T is the thickness of your samples. So we can obtain the current by this relation. And also the current density is, we can write this relation. We can use this relation several times. So by this relation, we can replace Vx by this relation. So we can drop the W here, and NTE is in a denominator, and IX BG. So we can define the Hall coefficient. Hall coefficient is the electric field to the y direction and the multiplication of the current density and the y field to the g direction, or we can replace this form, or if we put the result of VH here, we can obtain this result. The important thing is here N is the charge carrier density, and actually this is the Q, charge. So we can obtain by measuring the Hall coefficient, we can determine charge carrier density, how many charge carrier in your sample. That's very important in semiconductor applications. And also, what is the sign of a charge carrier? Yeah, if it is metallic system, the charge carrier is the electron. But in a semiconductor, they can be a hole, so they can be positive. Can be negative or positive, depends on the type of the charge carrier. So in an N-type semiconductor, where the electron is the dominant charge carrier, we obtain the negative value. But for the charge carrier Q, but in a P-type semiconductor, we can obtain the plus sign for the Q. So this whole measurement is very important in a semiconductor industry. They should define the charge carrier density and also what is the dominant charge. This very basic measurement technique. Depends on the if you have a positive charge or negative charge, you can obtain the different sign of the whole voltage. Okay. So this is the called the ordinary Hall effect. Ordinary. So this cartoon also explains the same things. So please remember that from the Hall measurement, we can determine the charge carrier type, can be positive or negative, and the charge carrier concentration. Okay, so there are so many applications of your Hall effect, and as you see in your YouTube clip, they can be used the magnetic field sensors, and also distance or the rotation sensors. For example, if we have a magnet here, and we can put the Hall sensor, and if the magnet is moving by the sideway, then we can detect the change of the Hall sensors. So you can using the position sensor to the Hall, or if we have a rotation with some permanent magnet, there is some Hall signal is changing, something like this. So you can count the rotation. And also you can measure the magnetic field and using the switching. So there are many applications of the Hall effect especially in automobiles. And also you think about that your smartphone. There are many sensors in your smartphone, and there is some called magnetic sensors. This screen is actually screen capture of my smartphone, maybe Galaxy S something. There are many sensors, and one of the important things is the magnetic sensors. They are also the Hall sensors. Okay, so the Hall effect is very important in many science and applications, and there are many kind of Hall effect. We call the family of the Hall effect. The previous one is called the ordinary one. That means we have an anomalous one also. or in other words, called the extraordinary Holy Pet. This Holy Pet occurred in a ferromagnet. In ordinary Holy Pet occurred in any kind of conductor. They don't need to be ferromagnets, but in a ferromagnet, we have a similar things happens in a Holy Pet, but the signal is much, much larger, usually 100 times larger. And there are other Holy Pet called quantum Holy Pet. And also, there is some fractional quantum Holy Pet, and they got the Nobel Prize. And also, there's a spin Holy Pet and spin quantum Holy Pet, and Scomion Holy Pet, topological Holy Pet, summer Holy Pet, Nasty Pet. There are many things. All those things happens when they measure the current to this direction and measure the voltage here. We can obtain some signals. But they all different whole family has a different physical origin. But the measurement scheme itself is quite similar. That's why we call this the Holy Pet. Okay. And as you see here, these two guys, the quantum Holy Pet and the fractional quantum Holy Pet, got a Nobel Prize. And this other family of the Holy Pet, who knows, they can obtain the Nobel Prize. That's why I put the question mark here. That's also very important in our scientifically and also in our applications. Okay. Okay, so I think I should conclude this lecture with some time for the questions. Yeah, please ask questions about the Stonewall Pass model or educations, or maybe you can ask about the Holy Path. So when I showed YouTube, is it okay? Can you guys see without any problem? Okay, good. How about the equation of the Stonewall Pass model? Do you think is it okay? There's no problem to understand? Okay, good. Yeah, actually, when you download any kind of sensor related app in your smartphone, there are many things. You can find such kind of app by the keyword of the sensor. Then it is surprising there are so many sensors in your smartphone. So you may check it. It is very funny. Also, there are more things. Maybe. Yeah, this is the Wikipedia what the Holy Pet, and there are many applications. And as I already said, there's a quantum Holy Pet, spin Holy Pet, quantum spin Holy Pet, on Pet, many things. And yeah, this cartoon I showed you in my lecture note. There's a same equations. Maybe this is also good. Can you see this animation? Good. This is also good animation to understand the Hall effect. Yeah, there are many applications. Any questions? There is no questions today? Okay. Anyway, I'm gonna upload the lecture note, and also we have one more homework about the storm pass model and the various energy chapter. Okay. Okay, then see you Wednesday. Bye, guys.